We've introduced this concept of the mole before. We've talked about the mole. The mole is just a number. And I really want to stay on this a little bit because I really want you to get the mole is just a number. We use this thing called a dozen, and we're talking about how many? 12. And we say a pair, and we mean two. And there may be something you may not have heard of called a gross. I would often have to go sharpen a gross of pencils.
An amount?
It's an amount. So a gross is a dozen, which would make it how many? A dozen would be how many? 144, right. So a dozen's 144. That's a gross. And there's lots of other words that we use to measure things. And this is what I want you to understand, that a mole is just a word that we use instead of a long, big number. Unlike 12 for a dozen, this number is really large. It's 6.02 times 10 to the 23rd. We introduced this a little bit last semester. We're going to come back to it. And we're going to stay on it over and over and over. I really want you to grasp how big a mole is and what a mole is. But if I tell you that I've got a mole of marshmallows, that means I have 6.02 times 10 to the 23rd marshmallows. And if I have a mole of donuts, it means I have 6.02 times 10 to the 23rd donuts. And if I have a mole of carbon atoms, I have 6.02 times 10 to the 23rd carbon atoms. That's what a mole means. Just like if I have a dozen eggs, how many eggs is that? 6.02. A dozen eggs. 12. And if I have a dozen cookies, it's 12. And a dozen donuts is 12 donuts. You got that? Mole is the same way. I will tell you on a practical level, we don't actually use that a lot once you get into the lab. But it's important for you to understand that if I have a mole of something, for instance, a mole of carbon, it has a mass, and that mass can be found in the periodic table. Just a quick summary of what we're doing today. And I don't typically talk about having an atom of carbon. It's really, really small, right? So I don't want to talk about an atom of carbon. Instead, we'll talk about a mole of carbon. And a mole of carbon is 6.02 times 10 to the 23rd atoms of carbon. And a mole of carbon has a mass of 12.01 grams. This happens to be a mole of copper. This is 6.02 times 10 to the 23rd atoms of copper are in this bag. Now, if that's the case, that means each atom is really, 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 really small. I did not sit down and count out 6.02 times 10 to the 23rd atoms of carbon. I did what? How did I get 6.02 times 10 to the 23rd atoms of carbon in here? I did measure, that's right.
By like the weight?
The weight, the mass. So if I have a mole of carbon, what would that mass be?
12.0.
Carbon, yeah, not carbon, copper.
63.55.
Yeah, so it turns out that this bag of copper is 63.55 grams. And I know, because I have 63.55 grams, that I have 6.02 times 10 to the 23rd atoms. Each atom is a little big, yeah.
Is the whole bag 63.55 or is
just the copper that's inside it? Yeah. So that's copper. Somewhere around here I've got silicon. Maybe. There it is. There's silicon. Now, a mole of silicon has a mass of
6.02.
that's not a mass, that's a count. Very important to know the difference. Silicon, what's the mass of silicon?
28.09.
28.09. So this is 28.1 grams, 1 mole of silicon. And I found that in the periodic table, right? Let's figure out I took the mass of a marshmallow, big marshmallow seed, and I measured it, and it was 5.70 grams. If I happen to have a mole of marshmallows, that's one marshmallow. I would multiply this by okay. Somebody punchy that for me. Write this up here where people can see. Marshmallow, 1 is 5.70 grams. So, if I were to have 2 times 10 to the 23rd, that's 1 mole of marshmallows. What would the mass of that be? What'd you get?
3.4314
4314
times 10 to the 24th.
grams. Y'all got that? I knew that was going to happen. All right. Let me look at this just for funsies. So, if I had a mole of marshmallows, this size, the big ones, right? If I had a mole of marshmallows, my mass would be 3.4314 times 10 to the 24th grams, right? So I just looked up on Google, and the mass of the Earth is 5.972 times 10 to the 24th kilograms. So you'd have to add another 3. So 10 to the 27th grams, right? So do y'all understand the scale we're talking about now?
Yes.
That if I've got that many marshmallows, this little tiny baby marshmallow, we're getting close, still off by a little bit, we're getting close though to the scale of the mass of the Earth. And what that lets us know is how small, just how small those atoms are, and how many of them it takes to interact. That's really one of the main points in chemistry. It's why we dig into the mole a little bit. One of the main points in chemistry, one of the things I want you to, in June of 22, so, a year and a half from now, if somebody walks up to you on the street and asks you about chemistry, I want you to know that the entire universe is made up of small particles and the interactions of those particles. That's lit. That's chemistry. I want you to get that the desk you're looking at is not one thing. It's a whole bunch of individual particles. That the air you breathe is a whole bunch of individual particles. That the processes that are going on inside your body is a bunch of chemistry and a bunch of individual particles that are interacting with each other on a very small scale. Okay? Very important. So in chemistry, we want to talk about numbers of atoms, molecules, or formula units. These things on an individual level are very, very small. And so we're going to use a large number to count them. We're going to call that Avogadro's number. Okay? And that is 6.02 times 10 to the 23rd. Yeah, those are not clean. Those are, so put the green bottles away, the things with the plastic rings. Yeah, what I'm looking for is the stuff that's really it's clean, easy to use, doesn't have extra stuff on it. All those things have ratings on them. Yeah, like that's stain. Look for the high class stuff. We're going to ship the rest over to storage. Okay. The mole is simply a word that represents a specific quantity. This quantity happens to be 6.02 times 10 to the 23rd. We do tend to abbreviate it as MOL. You kind of need to get used to that. You also need to remember that MOL does not mean molecule. Don't get confused. Something else. Give me another word that means a quantity. Dozen. How many does it mean? 12. What about another word? What?
Triple.
Okay. Pair would be 2. Few. All right, there's an official definition. How about, what else? What, gross? We talked about gross. Gross is how many? 144. We do this a lot. A lot of students come here and like this, they act like this is the first time they've ever heard it. They haven't. Dozens, a baker's dozen could be 13. It's that extra one they throw in there for you, right?
That makes no sense.
There's a fun little story you can look up about why there's such a thing as a baker's dozen. Okay? Yeah.
Would like the word 1,000 and 100 mean the same thing?
Well, those mean the same. Those are words for numbers. But like dozen, like because you would say 12 with the Arabic 1, 2 versus spelling out 12, right?
Yeah.
But dozen's kind of like, why do you have a word that represents a number? Mole is this really big number that you would hate to write out all the time. It's also a way we tend to deal with buckets, right? So buckets of stuff, right? We don't talk about drops of milk. How many drops of milk, right? You do a gallon of milk, right? Because you want to handle a gallon or maybe a half a gallon at a time. You don't buy your milk by individual drops. That would get really cumbersome. So you buy a gallon at a time. Chemists are the same way. You want to handle a mole at a time. So, all right. So a mole of anything contains 6.02 times 10 to the 23rd of that substance. So if I happen to have a mole of eggs, I have 6.02 times 10 to the 23rd eggs. And if I have a mole of donuts, how many donuts do I have?
6.02.
And if I have a mole of elephants, how many elephants do I have? Yeah, y'all are getting it. It's the same thing. If I say mole, you know it's 6.02 times 10 to the 23rd. If I have a mole of shoes, I have 6.02 times 10 to the 23rd shoes.
Would it be the same thing for everything?
It is. And that's what we're trying to get through to you. Just like if I have a dozen cookies, how many cookies do I have? And if I have a dozen eggs, how many eggs do I have? 12. That's what I need to get you. This is like seems to be the hardest part that students fight with. Is what's a mole? It's just a word that represents a number. Once we get to that point, then we can work on this. All right. I want you to write this down. If I have an element, except for our fun little friends, the diatomics, if I have an element, I'm going to call it an atom because we have moles of atoms. Ionic compounds are formula units. And covalent compounds we call molecules. Y'all get those? Pretty sure you've seen this before, but it's worth seeing again now that you've got this concept in your head.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you had equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind. Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Good grammar and spelling are important.
Yeah, cool. Good. Enjoying your first day back? Ready for your quiz? All right, remember your diatomics. Very, very important, your diatomics, right? How many diatomics are there? 7. You can remember it with Brinkelhoff if you like that. You can remember it, you can start with element number 7 and draw 7 and add the 1. That works too. Whatever works for you, you need to remember the diatomics. Because when I say chlorine, I need you to remember that that formula for chlorine is Cl2. And oxygen is O2. And hydrogen is, there you go. If that's all you can find, don't worry about it. Just make sure you go in there and find the places where they're supposed to be. Okay? So here's our, remember our diatomics. There's a line on your notes, I didn't realize it was there. It's just using the proper capitalizations. That's all that Brinkelhoff line is. Okay? Yeah, just scoot your desk a little bit. What's that? Diatomic.
What do we do here? I missed it.
This one? It's just the it's just the letters with the proper capitalization. So the BR with the lowercase r and the lowercase l, Brinkelhoff. And then diatomic molecules is the very first blank here.
We put +2 next to all these, right?
What do notes look like? Oh, and that's just the formula, like H2, N2, O2.
What's the schedule for today? Like, what is this class? Do we have legal test today?
No, that's what we did. We did basic homework. 10:56. So you're stuck with me for about another hour. I like that attitude. See. Good. All right. Let's talk about this now. Potassium. Formula for potassium is what? K. What kind of substance is that? If I'm just saying potassium. It's an element, right? It is a metal. It's just an element. If I'm talking about individual elements that are by themselves, that are not diatomic, those are going to be what? What do I call those particles? Elements that are by themselves and their smallest particles? Atoms, yeah. Atom. Magnesium chloride. In order to answer this question, let's come up with a formula here. Magnesium chloride is what kind of formula? Ionic or covalent? It's going to be ionic, so let's go ahead and do the crisscross. Magnesium would be Mg, and its charge would be +2, and chloride is Cl and -1. Again, I really, really strongly encourage y'all to go ahead and do this crisscross. You don't have to draw the arrows. So the formula for magnesium chloride is MgCl2. What kind of substance is this? It's an ionic compound, right? And the representative particle for ionic compounds are formula units. Remember, we write these as the smallest whole number ratio because they form crystal lattices. Okay, Let's look at diphosphorous pentoxide. Diphosphorous pentoxide, what kind of compound is that? It's going to be covalent. I'm going to go ahead and write that over here. This is going to be a covalent compound, and we call that a molecule. Molecule is what we're looking for. What is the formula for diphosphorous pentoxide?
P2.
If you're struggling with this, this is time to get your all your information renewed.
2, 3, 5,
Right, and then we write that. Right, diphosphorous pentoxide. The representative particle for that is the molecule you just said there. Molecule, right? How about fluorine? Formula for fluorine is,
F2.
y'all get that? It's F2. Fluorine's F2. So that's a diatomic element, and diatomic elements, because they're diatomic, would you call them atoms? No, you'd call them, they're also molecules. They're not compounds because they're not two different things sharing a covalent bond. They're the same, but they are a molecule. Good. Let's see if I made any mistakes here. I did okay. All right. We've done this. We're going to go back to, if you remember our dimensional analysis, one of the things we had to work with was equalities. We had to work with equalities. I'm going to take a second here. Let's blank this for just a second. Let's go back to our algebra days. If I tell you that A equals B, and I give you that as a definition, that A equals B, then A divided by B equals what? 1. And B divided by A equals 1. This is what lets us have dimensional analysis. What makes dimensional analysis work? Right? I'm not actually changing how much of something I have. I'm just changing how I represent it. We did this earlier with terms of seconds, right? If I said there's 10 minutes left in class, how many seconds would that be? 600, right? Y'all got there's 60 seconds in a minute. And I could say, somebody says, well, how much time's left in class? And I would say 600 seconds. And y'all would look at me like, what? Right? Because it would be probably more appropriate for me to say there's 10 minutes. But both of those answers are correct. They're both marking the same amount of time. It's just what units do you actually want to be working with. And for us, when we're talking about how many minutes are left in class, that minute seems to be the way to think about it. How much time's left in class, minutes seems to be the appropriate, right? If I said, how long is it till Christmas? Right? Maybe you think days is the best way, but probably not seconds. So maybe days, maybe months, maybe I just go, you know, it's roughly 12 months, 11 and a half months. So the amount of time is going to be the same. Yeah, I could go down to seconds and get a little more accurate depending upon when you propose Christmas begins. But the point of dimensional analysis is using equalities, using this mathematical rule that just converts units. That's it. So oftentimes that's of course why we call it unit conversion. All right. So we have an equality that 1 mole of any substance is equal to 6.02 times 10 to the 23rd particles of that substance. Therefore, I can make conversion factors that are algebraically true. 1 mole divided by 6.02 times 10 to the 23rd particles, or 6.02 times 10 to the 23rd particles divided by 1 mole. Both of those equal 1. And I'm allowed to multiply things by 1 in algebra because it doesn't change anything. Okay? Good? All right, very important. Let's now combine our 2 pieces of knowledge and let's solve some problems. So I'm going to take care of the first one. It's helpful because it lets us do shorthand. What's the formula for sulfur dioxide? What kind of compound is that, first of all? Covalent. Sulfur's a nonmetal. Oxygen's a nonmetal. But what's the easiest giveaway? The di. We used a prefix here. So the formula for sulfur dioxide is
SO2.
SO2. So here's what I want to say. 7.50 moles of SO2. Okay? Let's go to my equality. My equality says that 1 mole What kind of compound is this? We just said it. It's covalent. That means it's a formula unit, molecule, atom, donut. Molecule. It's going to be a molecule. I'm going to write this over the side. So 7.50 moles of sulfur dioxide. On the bottom, I've got 1 mole of SO2. 6.02 times 10 to the 23rd. Okay. Notice I'm going to get my, this is up here, right? Number unit stuff. This is number unit stuff, number unit stuff, number unit stuff. Y'all follow me? Number unit stuff on everything. Could be 2 liters of Dr. Pepper, 7.5 moles of sulfur dioxide. These two cancel out together. 7.5 times 6.02 times 10 to the 23rd molecules of SO2. Get your calculators out if you need it. Yep. I'll let everybody do the punchy. It's kind of fun. What's that? All right, now what did we get? Who had this?
4.515 times 10 to the 24.
4.515
515 times 10 to the 24.
Wesley, you get that? Okay. That's all I got. Go check with her and see what she got.
So we always get anything in scientific notation.
So sometimes it's going to make sense too. We're going to do a problem in just a second where it doesn't. Basically, if they're really big numbers or really small numbers, scientific notation helps. If they're like 3-digit numbers, you can just write it out. But numbers with a lot of zeros in the front or a lot of zeros in the back, you want to use scientific notation. It'll keep you from making mistakes. Okay, you guys go ahead and do the second one. Feel free to sit down or work on something else or whatever you need to do. All right, let's go through this. 0.400 moles. And potassium chloride is what? KCl. Because this is K plus 1, Cl minus 1, and crisscross, I get KCl, right? So that many moles of KCl. Potassium chloride is what kind of compound? Ionic, and so what do we use to talk about ionic particles? Formula units, yeah, there you go. So 1 mole of KCl is 6.02 times 10 to the 23rd formula units of KCl. Okay? So 0.4 times 6.02 times 10 to the 23rd is what? What's that? What do we get?
2.408
times 10 to
times 10 to the 23rd.
KCl. Everybody okay with that? See how that works? All right, cool. Let's take a look at the next one. If I happen to tell you that I've got 4.81 times 10 to the 24th atoms of lithium, how many moles do I have?
You have to divide it by.
We're gonna use the same process. 4.81 times 10 to the 24th atoms of lithium. Now, if I know that 1 mole of lithium is 6.02 times 10 to the 23rd atoms of lithium, I can write an equality. Which one of those goes on the bottom?
One more.
What goes on the bottom, guys? What am I trying to get rid of?
The 6 point.
Atoms, right? So the atoms is going on the bottom, so 6.02 times 10 to the 23rd, and 1 mole. Mathematically, that's allowed because this equals what?
1.
1. All right, so we get rid of atoms of lithium and atoms of lithium. Everybody should punchy this for me. And I want you to remember our good friend parentheses.
So you do.
So there's 2 ways to do this. We're gonna do the punchy way. I'm gonna show you the quickie, super shortcut way.
Would you divide instead of multiply, or are you still multiplying?
Yeah, so I'm multiplying across the top, and so this number times 1, and then dividing this.
Okay.
So it's 4.81 times 10 to the 24th. Use this little calculator thing. Divided by 6.02 times 10 to the 23rd.
What if you just get a number and a long decimal? That'd be right.
Sure. How many sig figs you gonna have?
38.
My original number. Original number has 3, so my final answer should have 3. There you go. And in fact, you should get. I think you get what? Okay. Everybody good with that? Blank that out. Everybody can read it. People at home can read it. All right. Here's what I want you to think about. If you don't have a calculator on you, this particular problem works out really easy. And here's what it is. I'm going to rewrite this together. 4.81 times 10 to the 24th over 6.02 times 10 to the 23rd. Okay? Remember, powers of 10 rule. I'm subtracting things out, right? So something I can look at, I should start being able to see, well, 48 and 6, that seems familiar. 48 divided by 6 is what? 8. So here's something I can do. I can actually change this. 48.1 times 10 to the 23rd is the same as 40.8 times 10 to the 24th, yes? Now my powers of 20, these go away. 48 divided by 6 is pretty close to 8. And oh, it's pretty close to 8. Now you could have also done that with simple subtraction, right? You could have ended up with 0.8 times 10, right? Which would have gotten you to the same point. Or 4.8 divided by 6 is 0.8, right? All right, cool. But paying attention to these powers of 10, because like this is a totally fair question to give you on a multiple choice. Totally fair question, a multiple choice with no calculator. Okay? Which we may start, not probably some of the stuff after spring break we may go to. Definitely next year, in your multiple choice tests, most of the multiple choice portions are not going to have a calculator. So you need to be able to do some of this mental math stuff. So I'm trying to show you some tricks as we go along. But learning some of the powers of 10 tricks are really going to help you out. All right. You guys do the next one. Or harder. Okay. Or we, yeah, go ahead. If we do this and we punchy, what do we end up with?
564.8 moles.
560 moles, right? Of NO2. And how many sig figs do we have here? 2, so my answer should have 2, and 560 gets me 2 sig figs. Good? All right. So we can go forward and we can go backwards. Let's talk about this thing that we've already talked about. We're talking about this thing called molar mass. Now, molar mass is simply the mass of a mole of a substance. So we went over the mass of a mole of marshmallows, right? I figured out how many. So the molar mass of carbon, you can look at your periodic table and find out. If I happen to have a mole of carbon, I have 12.01 grams of carbon. Everybody have a periodic table on your desk? You okay? All right. If I have a mole of aluminum, how many grams do I have? If I have a, how many?
26.9.
26.98. 26.98. That's how many grams of aluminum I have if I happen to have a mole of them. Okay? So a mole of carbon is 12.01 grams. I want to add this because it's really important you keep these guys together. .02 times 10 to the 23rd atoms of carbon is a mole of carbon, and it has a mass of 12.01 grams. Those are all the same thing. They are equivalent to each other. They mean the same thing. So I could give you moles, I could give you molecules. Either one, you can tell me how many grams I have. I can give you grams, you can tell me how many moles I have. And from how many moles I have, you can tell me how many molecules I have. Okay? Really important concept. I do want you to note the units for molar mass is grams per mole. We very frequently, almost always have a test question where we just ask you straight up, it's a simple question, what are the units for molar mass? Grams per mole. Okay? How do I know this? Well, I know this because I look at the periodic table, and the numbers on the periodic table actually tell me the molar mass. I know we told you it's A and U, it's the same thing. The digits are the same. The numbers mean the same thing. Yes, it's 12.01 average atomic mass units. It's also 12.01 grams per mole. All right, how do I find molar mass? We have actually done this before. We did this in a previous unit. And so in order to find the molar mass, the first thing I have to find is the formula. What's the formula for zinc? What is it? And the molar mass for zinc is
65.38.
3.8.
Yeah.
Okay. And we're done. Zinc was easy.
Chlorine is a diatomic.
That's right. So the formula for chlorine is Cl2. And so I'm going to write this. I'm going to molar mass for chlorine is
35.453 times 10.
and so the molar mass for chlorine, Cl2, would be, you do not need a calculator for that. And notice how I'm very carefully keeping up with my units. The molar mass for chlorine is 70.90 grams per mole. Calcium bromide. Now calcium bromide is what kind of compound? It's ionic. And so in order to find the formula, we need to write the symbols and the charges and crisscross, right? Calcium bromide, calcium symbol is
Ca.
charge is bromide is charge is, and I crisscross those, and my formula is, and I really want you for the rest of this unit to break it down. When I ask you to show me the work, show it to me. So calcium, how many calciums do I have?
40.1.
How many atoms do I have?
One.
Got one of those. And it has a molar mass of 40.08. Okay? We'll come back to that. How many bromines do I have?
2.
2 of those, and it has a molar mass of,
79.90.
okay, so I can do the first one for you. And the second one would be what?
159.8.
What is it?
159.8.
And so the molar mass of calcium bromide is 199.88 grams per mole. You guys do the next one. All right, so magnesium phosphate, the first thing we need to do is get the formula. Now, what kind of compound is this going to be? Ionic, right? So magnesium symbol is, and its charge is going to be,
+2.
phosphate's formula is
PO.
4, and its charge is -3, and so I crisscross these, I end up with Mg3 PO4 2. And obviously if you mess that up, the rest of it's going to be a mess, right? So we got to make sure you get that right. So this is Mg. We've got 3 of those, and the molar mass of magnesium is 24 point what?
0.30.
Okay. And how many phosphorus atoms do I have in each one of these formula units? We've got 2 of those, and that is 30.97.
97.
What y'all said? Is that right? And then oxygen, how many oxygens do I have?
18.
Okay. And we multiply all these out. And this 3 times 24.30 is 72 point what? 0, okay. And this one is
61.9.
add all that together. 4, it's okay, 1. So it should be what, 2, 6, and 2. Is that right? Did I mess something up here? Are we okay? 262.84 grams per mole. Everybody get that? We okay? Okay. Y'all good with that? Any questions? No questions. All right, so homework is going to be pages 1 through 3. You have an opportunity to finish that in class. Okay? So we're going to go ahead and stop there. Again, homework is going to do pages 1 to 3 for homework. Yes?
So R2 is 8 because you multiplied 2 times 4.
Right, that's correct. 2 times 4. Another way some people do this is to solve the molar mass of a phosphate and then multiply by 2. I just typically pull them all out all the way. Because I did the same thing, so this is 2 times 1 phosphorus.